Let my computer figure itself out. This will be entertaining. I got a little tiny screen on my computer to look at, my big one up there. Okay, so section 2.3. Nope, that's not going to work. I have to change this. So I was trying something different. Oh, pop it up. I was trying to just share the one thing, but that's not going to work because I can't fast forward the slides. Section 2.3 begins with a definition. Let me get my book open. Oh, this is my definition I put up here. It says let f take d to r and g take d to r. Define f plus g to be f of x plus g of x. F times g is f of x times g of x. F divided by g to be f of x over g of x. For all x in D where g of x is not equal to 0. It should. We've already done this before in limits, in sequences. Okay, we're looking at exercise 2. This is number 21. It says, suppose that G takes D to R. Oh, let me get it out from underneath my little hand.
Just to clarify, G is just a normal.
It's a function, yeah. Yeah, whenever we use this notation, that's telling you, you know it's a function.
And R is
R is the reals. No particular reason. It's just familiarizing you with all the notation that's used. Yeah, and so J and R, J is for the integers, yeah, natural numbers. R is the reals.
I like it better because a lot of times they say like lowercase and then capital N, and that is the natural N too, so I just use it.
There you go. Not confuse the ends up. Okay, suppose that G takes D to R, x naught is an accumulation point of D, and G of x is not equal to 0 for all x in D. Assume that G has a limit, and that the limit as x goes to x naught of G of x is not equal to 0. Show that there exists an M in the reals, positive reals, in a neighborhood Q, such that for all x in Q intersected with D, G of x is greater than or equal to M. So we have a lower bound. We call this bounded away from 0. So show that G is bounded away from 0. What's the hypothesis? Yeah, the first little bit. Yeah. Suppose G takes D to R. X naught is an accumulation point of D. And assume that G has a limit. What should we call the limit? What do you want to call it? L. I heard L first, sorry. So L with L not equal to 0. Now we have to find the M. So this is this last part, the then on, is what we have to show. So we have to find the M and a neighborhood Q so that g of x is greater than or equal to M for all x in Q. Well, Q intersected with D. Well, the only thing we have is that we know that this limit exists. So that means we're going to apply that definition. I'm going to actually make it be L over 2 because I know the limit is L. Well, I have to bound it away from 0. And so I know that the limit is not 0. And so if I make that region, in other words, here's what I'm thinking of. Here's my L, and I know that I'm approaching some value here at x naught, at L. So if I have L over 2, then the limit has to be in this region for some delta values down here. So I could have something that looks like that. And so inside these x values from here to here, I know that the g of x is bigger than that lower bound of L over 2, right? So that's why I'm choosing epsilon to be L over 2. It gives me a lower bound. Then, since L is not equal to 0, epsilon is greater than, well, epsilon is not equal to 0. We're going to have two cases where that's positive and negative. Maybe I should split it up right now because I do my picture for it positive. Let me do that. I hate erasing things, but I'm going to do that. I think it'll be easier for you guys to follow it rather than me trying to prove both cases at once. I know epsilon is greater than 0, and since the limit as x goes to x naught, g of x is equal to L, I know that there exists a delta greater than 0 such that for all x in D, with 0 less than x minus x naught less than delta, we have g of x, not f of x. G of x minus L has to be less than epsilon. Now, we have to figure out what our capital M is going to be. So what do you think we should do to try and, we need to get a g of x all by itself. So apply the definition of absolute value. By the definition of absolute values, I know that there exists, let me do it this way. I won't skip steps. Are we good with that? We want to get g of x by itself. Any ideas? Yep. But what was our epsilon chosen to be? L over 2. So L minus L over 2 is less than g of x is less than L plus L over 2. L is positive. So tell me about L minus L over 2. It's L over 2. And then that would be 3L over 2. It's all greater than 0, so then that tells you that g of x in absolute value is greater than or equal to L over 2, right? That's what we wanted. So in this case, that is the M, is L over 2. And now we have to figure out what that Q was. Remember, we were looking for a Q. We have to figure out what that Q should be. I would submit to you that Q is going to be the interval x naught minus delta to x naught plus delta. Yeah, then for all x and q intersected with d, you're going to have g of x is greater than L over 2 if x is not equal to x naught. And the absolute value of g of x naught is going to be greater than 0, because I know g of x naught was not equal to 0. That's what they told us, right? I'm not getting my two things confused, am I? No, they didn't tell us g of x naught. Sorry. That is going to be in a minute. We'll talk about that. So that's bigger than our bound, and we're going to choose M to be that bound for this case. Now let's look at case 2. This would be L is less than 0. So we're going to choose epsilon to be equal to the absolute value of L over 2. Then there exists a delta. This up here should be a delta 1 now because I've got a delta 2. I've got another delta floating around. So let's go make these all delta 1s. And down here, we're going to make this a delta 2, such that for all x in D, with 0 less than x minus x naught less than delta 2, we have, and then you're going to have g of x minus L is less than epsilon. Well, apply your definition of absolute value. You're going to have minus epsilon is less than g of x minus L is less than epsilon. Add your L. But what was epsilon? Remember, this L here is negative. So that absolute value of L is negative. So you're actually subtracting. This is a minus number and then minus half of that. So that's going to be minus 3/2 absolute value of L. And then over here on this side, this would be absolute value of L over 2, right? Because I'm adding it to a negative value.
Would it be negative?
Yes.
Absolute value of L.
Negative absolute value of L over 2. So that tells you that G is negative. So what happens to the absolute value of G then? Yeah, and in fact, it's going to be bigger than the absolute value of L over 2, right? Here again, we have to choose our Q. So choose Q to be equal to x minus delta 2, x plus delta 2. These are x naughts. Then for all x in Q intersected with D, we have g of x in absolute value is greater than absolute value of L over 2 if x is not equal to x naught. We only have one other case to look at, and that is if g of x, if x naught is in D, then our maximum, we have to check and see if g of x naught is smaller than L over 2. So what we're going to do right here, I guess let me summarize the two cases. From the two cases, choose Q, choose delta to be the minimum of the two deltas, and Q to be equal to x naught minus delta to x naught plus delta. Choose M to be the minimum of absolute value of L over 2 and g of x naught in absolute value if x naught is in D, or M to be just absolute value of L over 2 if x naught is not in D. Because you have to choose it. If g of x naught is smaller than L over 2, which I could argue it's not going to be, because that's where our limit is, but maybe there's a jump in our function or something, then we have to take into consideration that that might be smaller than our value of L over 2. But we still know that it's not going to be equal to 0 because everything in that region was non-zero. So it can be bounded away from 0. By hypothesis, if x naught is in D, then g of x naught is not equal to 0. Thus, M is strictly bigger than 0. And so, for all x in Q intersected with D, we have g of x in absolute value is greater than or equal to M, as desired. That's an argument we've actually sort of made before. You know, put the epsilons on both sides, add your limit to both sides, and then find a lower bound for your function. So we've made that argument before. Now the whole reason that we do this is that this is telling us that we can bound our function away from 0. And we need that for our division when we're talking about our division problem for our limits. So let's go look at our theorem. It says, suppose f and g take D to R with x naught an accumulation point of D. And further, suppose that f and g have limits at x naught. Then the limit of f plus g, notice this could be plus or minus. You just put appropriate minus through there. You can do it that way. So f plus or minus g has a limit at x naught, and the limit of f plus or minus g is the limit of f plus or minus the limit of g. F times g is a limit at x naught, and the limit of f times g is just the limit of f times the limit of g. And then the division is a limit of f divided by the limit of g, assuming that g of x is non-zero. The limit of g of x is non-zero. They should be very familiar. We had them for sequences. We're going to prove them. We're going to, yeah, exactly. We're going to prove them just like we did the last one. Suppose, what's our hypothesis here? Yeah, that whole first part. Let f and g take D to R with x naught an accumulation point of D. And I'm just going to say limit as x goes to x naught of f of x. We're going to call that A. And limit as x goes to x naught g of x, it's going to be B. Yep. Now, let's just run through these to prove part one. First of all, let's go ahead and write down what our definition is. Well, we're going to need a different one for each one of them. I could put that epsilon at the beginning, but I'm going to have to restate the deltas anyway, so I'll just redo each proof. So fix epsilon. We know that the limits exist, so by definition of A and B, well, I'll do one at a time. By definition of A, there exists a delta 1 greater than 0, such that for all x in D with 0 less than x minus x naught less than delta 1, we have f of x minus A. I'm betting I'm going to need an epsilon over 2. So I'll put that there. Yep, we want it to go away. By definition of B, there exists a delta 2 such that for all x in D with 0 less than x minus x naught less than delta 2, we have g of x minus b. What do you think we need? Epsilon over 2. Yep. What should we choose our delta to be? We have a delta 1 and a delta 2. We need to choose a delta now. Yeah, choose delta to be the minimum of delta 1 and delta 2. Then for all x in D with 0 less than x minus x naught, my computer catch up, there we go, less than delta, we have, I'm doing the addition. It doesn't matter if I do addition and subtraction, so I'm going to put them both together. F of x plus or minus g of x minus a plus or minus b. Split them apart. This is going to be f of x minus a plus or minus g of x minus b. What should we do next? Yeah, triangle inequality. Well, you're one step ahead of me. Triangle inequality, then substitute. So that's f of x minus a. Notice when you do the triangle inequality, this plus or minus right here just becomes a plus. Because the absolute value, the minus doesn't pass through the absolute value. It doesn't matter if it's plus or minus. Yeah. B minus A?
No, like A plus B is less than A minus B.
Oh, that's a different one. I'm not using that one. That one has absolute values inside of absolute values. It's a little bit different. Okay, so then this becomes g of x minus b. But what is each one of these smaller than? So what do we conclude? That's the first one. Yep. The multiplication one's a little bit harder. I'm actually just going to go to the division one. The multiplication one is in the book.
Division one's not.
They're both in the book, but they do it differently. They actually do sequences for it. And I want to go back to that epsilon delta proof. I want to reinforce that method. See book and notes for sequences. In chapter 1. We did that. So let's look at 3. Notice what they give us for the hypothesis here. It says g of x is not equal to 0 for all x in D, and the limit as x goes to x0, g of x is not equal to 0. So I know that b is not equal to 0. Okay, now we proved a theorem, first one that we did, just, not 10 minutes ago, that gave me a bound for this. This is homework number 21. I know that there exists a Q. I'm going to write it out.
Theorem is
Yeah, but I've already proved it, so it's not a homework problem you have to do. But it is listed in the book as a homework problem. There exists a neighborhood Q and an M in R plus such that for all x in Q intersected with D, g of x in absolute value is greater than or equal to M. R plus means that M is not equal to 0, so this value right here is strictly bigger than 0. That's going to be important to us because we're going to have some division issues. Now, what we're going to do is fix our epsilon greater than 0. By definition of A, I know there exists a delta 1 greater than 0, such that for all x in D, with what? Definition of a limit.
0.
X minus x naught less than delta 1. We have f of x minus a is less than something. We'll figure out what that something is. It's going to be a function of epsilon, but I don't know exactly what it's going to be yet. It's going to be epsilon over 2 times something. It's going to have some constant in there. By definition of B, I know that there exists a delta 2 greater than 0, such that for all x in D, with 0 less than x minus x naught less than delta 2, and this is going to be our g of x minus b is less than, here again, something. We'll figure that out when we know what we need it to be. By definition of Q, by definition of a neighborhood, I know there exists a delta 3 greater than 0, such that x naught minus delta 3, the interval, that's an x naught, not a b, x naught minus delta 3 to x naught plus delta 3, I know that that is contained in Q. What should we choose delta to be equal to? Has to work in all of those cases. The minimum. Choose delta to be the minimum of delta 1, delta 2, and delta 3. And so for all x in D with 0 less than x minus x naught less than delta. And now we're going to do some arithmetic. Unfortunately, it's not going to fit right there. Let's get another page. Okay, we have, and we'll start right here, f of x over g of x minus a over b. What should we do? Get a common denominator. So this is f of x times b minus g of x times a all over g of x times b. Now we have to add and subtract something. Any suggestions? Let me split it. Well, yeah, I'll split it up. B f of x minus, how about a b g of x, so I can factor out that first b, plus b g of x minus a g of x. The absolute value through the numerator and denominator. What should we do next? Do what? That adding zero is the technical term that they use. Yeah. Mm-hmm. Yeah, well, it's just adding zero. Mm-hmm. I just personally call it adding and subtracting. Yeah, okay, so absolute value. You can let me skip that step of factoring out that b. I wanted to be a here because I need an f of x minus a. Got the wrong one. So f of x minus a plus, over here you bring the a out. You have g of x minus b. Now, this is going to be right here. We had our g of x in absolute value was greater than or equal to m. That says that 1 over m is going to be less than or equal to 1 over the absolute value of g of x, right? So I can take care of this guy right here. That's going to become Rm. So this is less than or equal to absolute value of b, absolute value of f of x minus a, plus absolute value of a, g of x minus b, all divided by the absolute value of b and m. Now, I'm dividing by this b right here, but they told me that that b is not equal to 0. So I don't have to worry about my denominator being 0. Both of these are bounded away from 0. That's not equal to 0, and this is going to be replaced with this m, which is also bigger than 0. So I know I don't have division by 0 issues anymore. I'm going to split up my fraction, and for the first one we get f of x minus a in absolute value just divided by our capital M, correct? Yeah. And then the second one, nothing cancels. We get absolute value of a over the absolute value of b times our capital M, and then we have g of x minus b. We would like this first part to be an epsilon over 2, and I would like the second one to be an epsilon over 2. So let's take care of the f of x one. What do we need? We had, this is our scratch work again. Yeah. So we need epsilon m over 2. Then that cancels with that m right there. Maybe I should put a little bit more space here. This would be epsilon m over 2 divided by m. The m's are going to cancel, and you're going to get your epsilon over 2. Now for the second one, yeah, But no one told us the absolute value of A was not equal to 0. Add 1 to it. Now you know it's not equal to 0. You don't have division by 0 problems right there. So add 1 to it. And then you have all of that times this A over B stuff at the beginning. Let me see if I can't squeeze that in. So you know the M is going to cancel, the absolute value of B is going to cancel. The A over A plus 1 is less than 1. So then that's going to be less than absolute epsilon over 2 plus epsilon over 2, which is equal to epsilon. So let's go back up. We have epsilon M over 2 for this one. Where did we define our M? It's above. Yeah, we're good. And then this one was, I forget. B M over A plus 1. So that gets us what we need right there. And then we can go down and what is our conclusion then? Mm-hmm. That's all 3 of them. We skipped the multiplication one because the division one sort of has a multiplication work involved in it. You have to add and subtract and then cancel. Okay, suppose F takes D to R and G takes D to R. X naught is an accumulation point of D and F and G have limits at X naught. If f of x is less than or equal to g of x for all x and d, then the limit of f is less than or equal to the limit of g. This has a special name, this theorem. What do you think that name was? Squeeze theorem. Let's see if we can prove this. Yeah, that's where we often use it. Mm-hmm. Suppose f takes d to r and g takes d to r. X naught is an accumulation point. Of d, and limit as x goes to x naught of f. What do we want that to be? What do we want to call it?
L.
Okay. Limit as x goes to x naught of g is going to be what?
L1.
We can't have 2 L's. They have to be different. If you want to make that one L1 and this one L2, we can definitely do that. What we have to do is show that L1 is less than or equal to L2. We know one other thing. Suppose f of x is less than g of x for all x and d. Now, what I'm going to do is proceed by contradiction. Yeah. Well, limit of f of x is L1, so assume L1 is bigger than L2. Well, if L1 is bigger than L2, then I'm going to define an epsilon to be equal to L1 minus L2 over 2, which is some positive value. By definition of L1, I know that there exists a delta 1 greater than 0 such that for all x in D with a 0 less than x minus x naught less than delta 1, we have f of x minus L1 is less than epsilon. By definition of L2, I know there exists a delta 2 greater than 0 such that for all x in D with 0 less than x minus x naught less than delta 2, we have g of x minus L2 is less than epsilon. Let's break them down. Let's do g of x first. I'm going to have minus epsilon is less than, can I skip straight to this step? L2 minus epsilon is less than g of x is less than L2 plus epsilon. We've done that so many times, we should know that process by now. And, oh yeah, I'll use an and. And by definition of epsilon, I know that L2 minus L1 minus L2 over 2 is equal to what? That part we don't care about. No, that part we do care about. What is that equal to? Which is between L1 and L2, right?
Right.
Yeah. Yeah, 3L2. It's the other one I need.
3L2. No. No, that should be a negative 2L2 minus L1.
Don't you mean L1?
No, I want to get the average. I want an L1 plus an L2.
Oh, okay. Never mind.
Yeah. So that is, so I actually did the wrong one. So let's do the other one. There, we don't, in proofs, we don't put any extra work than we absolutely have to. So let's do the other one. How did the two equal signs get left? So let's look at L2 plus epsilon. That's equal to L2 minus L1 minus L2 over 2. These are plus. Plus L1 minus L2 over 2, which is L1 plus L2 over 2, which is actually the average, right? And so you have g of x is less than or equal to, in fact, it's strictly less than L1 plus L2 over 2. Similarly, let's run through the steps. I'm going to have L1 minus epsilon is less than f of x is less than L1 plus epsilon. And L1 minus epsilon is equal to L1 minus L2 over 2, which is 2L1 minus L1 plus L2 over 2, which is L1 plus L2 over 2. Thus, f of x is bigger than L1 plus L2 over 2. Putting these together, this is 1 and this is 2. Not quite equal. Oh, the L1 plus L2 parts are equal. What you get is g of x is less than L1 plus L2 over 2 is less than f of x for all x. We have to get our delta together. So this is why I like typing better than writing. I forgot my delta. Let me put my delta in here. Let delta be the minimum of delta 1 and delta 2. Then for all x in D, with 0 less than x minus x naught less than delta, we have g of x minus L2 is less than epsilon, and f of x minus L1 is less than epsilon, which means by 1 and 2. And here's our conclusion. Means that g of x is less than L1 plus L2 over 2 is less than f of x. But what was the hypothesis for this one?
G of x is greater than f of x.
Yeah, g of x is greater than f of x. And what have I just said?
So the opposite.
I said g of x is less than f of x, which is a contradiction, yes. Thus, I know that which one did L1 go with? L1 went with f of x. L1 is less than or equal to L2, as desired. Squeeze there.
That gonna be on this?
Why not? It's such a nice theorem. It's relatively easy to prove. Proof by contradiction. I don't know if it is or not, but it's a good one. I like it. And we use it a lot, especially in calculus. So that in your book is actually theorem 2.5. They actually leave that proof as exercise number 20. So I just did that one for you, but it's not actually a homework problem, but that makes it fair game for a test. That does make it fair game for a test. Okay, let's look at an example. Consider the function f of x equals x sine 1 over x. Use theorem 2.5 to find the limit as x approaches 0. So what's an upper bound for this? X sine 1 over x is less than or equal to x, right? And it's bigger than what? Negative x. Sine can go negative, so it's negative x. So what that's going to tell me is that the limit then is going to be what? Take the limit of each side. Limit as x goes to 0 of minus x is less than or equal to the limit as x goes to 0 of x sine 1 over x, which is less than or equal to the limit as x goes to 0 of x. Where does the first one go? 0. Zero. Yeah. Yeah.
Because they like split it up as an f and g function and use the multiplication, right?
That's in when we did in the last section. We did this in the last section and did do that.
Oh.
Wait, no.
I thought they did that also.
They might have actually.
Oh, maybe.
I think they did that in a different example.
Okay.
Because then they said refer back to the previous example. So
Maybe.
yeah, I skipped it because that was painful. Mm-hmm.
Is that by squeeze through?
By the squeeze theorem.
That's 2.5.
Yeah, 2.5 is the squeeze theorem.
Oh, I did just say
Yeah.
that. It's more known, more widely known as being 2.5.
I don't know why. They've named most of them, but they didn't name that one.
Because that's another question I was gonna ask you. For like theorem 1.2 or like theorem whatever, is that the same in every single analysis? Yeah, so sometimes I feel like that notation is the best.
It is because if you're trying to reference a theorem in this book, then you have a number to reference it by.
Well, sure, but like, what if you're talking to someone else who? doesn't
Then
know
you just state the theorem. You state this. This would be why in most journal articles, you'll have a preliminary section where they'll list all the definitions and theorems, and they'll give them all numbers. And then throughout the rest of the paper, they'll refer to those numbers.
That's why.
Yeah.
Is that what we should use our history math papers?
Yes.
No one ever.
Maybe I should not do. Who knows?
Well, you have another opportunity. It's coming. Okay, this is theorem 2.6 from your book. It's on the bottom of page 74. It says, let f take d to r and g take d to r and x naught be an accumulation point of d. If f is bounded in a neighborhood of x naught and g has a limit 0 at x naught, then f times g is a limit at x naught and the limit is 0. Okay, so let's look at our proof. Let's let the computer catch up. There we go. What's the hypothesis?
First sentence.
And then the F y.
Accumulation point.
Now, for the next one, I'm going to assume there exists a neighborhood Q of x naught such that f is bounded on Q intersecting with D, and assume that G has a limit. Let's
What is that? NBHB again?
neighborhood.
Neighborhood.
Sorry, I just get tired of writing after a while. Now, fix our epsilon bigger than 0 because we're trying to show that this limit is actually going to be 0. So fix epsilon greater than 0. I know that there exists a neighborhood Q of x naught so that f is bounded by hypothesis. I know there exists a delta 1 greater than 0 such that x naught minus delta 1, x naught plus delta 1 is a subset of Q, and f of x is less than or equal to sum m for all x in Q intersected with D and sum m in the positive reals. That's what it means to be bounded, smaller than some positive value. Now, the limit of g of x is equal to 0. So by definition of limit as x goes to x naught, g of x equals to 0, I know there exists a delta 2 greater than 0, such that for all x in D was 0 less than x minus x naught, less than delta 2. I wonder if I can squeeze that in there. I can. We have g of x minus 0 is going to be less than, we'll just call it epsilon. I think I need epsilon over m, but we'll come back and fix it. What should we choose our delta to be equal to? We have a delta 1 and a delta 2. Minimum. Deltas are always the minimums. Then for all x in D with 0 less than x minus x naught less than delta, we have, first of all, f of x is less than or equal to capital M, and g of x minus 0 is less than epsilon. Thus, let's look at the multiplication of this. We're just trying to show that f times g goes to 0. So f of x times g of x minus 0. What is that equal to? F of x times g of x. It's not rocket science yet. Seems like a trick question. I know. I'll let you ponder it for a minute. So many of my questions are trick. Uh-huh.
Because there are too many answers to that. Because that is also.
Yeah. I need epsilon over m. And so I should change that up here too. I have two of them where I make my first definition for delta 2. Oh yeah, right there. That was the other one. So there's our epsilon over m. So then that's less than m epsilon over m, which is equal to epsilon. What's your conclusion? Yeah. F times g is equal to 0. I know, it's gone. It scrolls. That is the one problem with writing it on the computer, but I think that's more important to have it on the computer and have you guys have the notes later than to put it on the chalkboard.
Oh, yes.
That's right.
I use this all the time when I'm doing
Mhm. I still do in set theory.
Oh.
I don't in the rest of it because my goal in set theory is twofold. I want to teach you LaTeX and I want to teach you how to write proofs. So yeah, I do type it LaTeX in set theory. But by now you should know LaTeX.
Near the end that people started.
Well, you know, when you get the new and improved version.
Unless you have a new version, yeah, that.
Yes, that's happening next semester. I thought about, they have made a new version for LaTeX that is Mac friendly, but it is. They tried you're actually writing everything in XML and then they convert it to LaTeX from XML. And it's not, it works totally differently than the one we're used to. You can do so much more with our program than how they've changed it. But you have infinite undos in the other one. I don't know if that's.
That's what I like.
Wait, why do they limit the amount
This is the main reason.
That's a LaTeX limitation. That's one of the reasons they took it out of LaTeX and put it into a web environment. That is a LaTeX limitation.
The other thing I like about this version a little better is that you can. space-
Oh, sorry, Elizabeth.
No, it's okay. I'll get it.
You're done? Okay. Yeah, you can. Okay. These are supposed to be split up onto 2 pages. Oh, well. Where does the function f take r to r defined by f of x equals a and x to the n, etc. have limits? What is this, by the way? If I write this whole thing out, we call it a polynomial. Hey, so where do polynomials have limits? If you think about your pre-calculus days and graphing polynomials, high school for some of us,
College.
yeah, they have limits everywhere. They're never undefined, right? Well, you can sort of figure this out by writing your polynomial function. First of all, you have the constant function. If you have g of x equals to a0, this has limits everywhere. If you write k of x to just be equal to x. This has a limit everywhere. Now, if you think about each polynomial function, if you look at f of x, you would have f of x is equal to g of x is, we'll call this some g0. So you'd have g sub n of x, which would be our a sub n. And then you're going to have k of x multiplied together n times. Each one of these is a limit everywhere by our previous multiplication theorem. You can multiply things together n times. So you could use induction to show that this limit is everywhere. We're not going to do that. But that would be your method you would use.
I can see why you would do that.
Mm-hmm.
They should make a theorem about that.
Get a different analysis book. There are some that have that as a theorem. Which meant I would have to prove it, and I really don't like doing that induction proof. It's very boring.
As well, where just be like this is proved,
Yeah.
not test it. Is it everywhere or everyone?
Everyone.
As a limit?
Everywhere. There we go.
The other vision.
The other version better.
Everyone. Everyone has a limit.
Every
Yeah.
single one of
That's the
the
truth.
X value limits.
So now we can show what we knew from pre-calculus. Oh dear, yes. And then let's look at example 8. It says let f of x be a polynomial of degree n and g of x be a polynomial of degree m. Determine those points x and r for which the rational function has limits. The limits are going to be everywhere except the zeros of g of x. That's by our division theorem that we're doing. It said the limits had to be non-zero. So everywhere that g of x is not equal to 0. Mhm. Pre-calculus. We just went over that last couple of days in pre-calculus. Except they don't know limits, so we're just talking about graphing for them. But yes.
What's sad is when they come into tutoring, I still have no idea what they're doing. Sometimes with the graphs.
So tell them to, if they're in my class, tell them to look up the notes online. I post all my notes online. You can look at them.
I always tell them, did you look on my hand?
Yeah, always tell them to look online. And then tell them that you need to read over it so you know how I taught it, because there's multiple ways to do it. And there are multiple ways to do it. So that's a great excuse. I used it all the time when I was tutoring. Especially in statistics, because I'd forget statistics so fast.
I kept-
statistics in our night.
Because I kept all of my notes from statistics,
Okay.
and so none of the other tutors except for
I have mine,
Michelle.
but I don't bring them.
Michelle kind of knows statistics, but basically I'm the statistics tutor
There you go.
because I have all the notes.
I can't remember if I really tried, but she knows it so much quicker. So I'm just like,
There
"Ugh."
you go. Go to the bench.
I tutored somebody on it last semester.
So it's sort of
and
fresh
this
in your
semester,
mind.
And so it's just still like hitting refresh.
Yeah. Still very refreshed. Okay, so look at this function right here.
That lovely fun.
It says use theorem 2.4 to find this limit as x goes to 0. So theorem 2.4, let me remind you which one that one was. Theorem 2.4 is the one where we have our division, addition, and subtraction and multiplication of limits. So if we define f of x to be the numerator, f of x is going to be the square root of 4 plus x, and g of x is that going to work? What is the limit as x goes to 0 of g of x? 0. So this doesn't work for the division, so we can't do it that way. So what should we try then? They rewrote it, yeah. Do you remember what they did?
They multiplied
Multiply
by the
By the conjugate, yes. Square root of 4 plus x plus 2. And now you can, in the numerator, what does this become? 4 plus x minus 4. So you get an x divided by, ending your denominator, you just are going to have this x square root of 4 plus x plus a 2x.
one over.
Yeah.
It's gone, it's 1 over, that's gone.
Now, so this part becomes our f, this part becomes a g, and you can take the limit now as x goes to, yeah.
Cross out the x's.
Cross out the x's, yeah, okay. I was missing something. Yeah, sorry, I multiplied it through, so you get 1 over 4 plus x plus 2. So this is f, this is g, so it's going to be 1/4. Yeah, we did that a much longer way last time. Yeah, we did.
Question.
No.
Yeah,
How can we explain some people that you cannot separate that apart? Whenever they see 1 over.
plug in
over
numbers.
something,
Plug in numbers like 2, 3, and 4, and make them add and subtract it. And you'll see it. That's the only way to do it.
They saw that they all want to separate it apart. Can you separate it apart?
The answer is no. Okay, really quickly on this one, show by example that even though f and g fail to have limits at x0, it is possible for f plus g to have a limit. So if I choose f of x to be equal to 1 over x and g of x to be minus 1 over x, then f plus g, plus g. What is f plus g? 0. That's going to have a limit. So that shows f plus g can have a limit. Give one for f times g.
1.
Yeah.
Negative 1.
I'm actually going to define it this way. -1 for x bigger than or equal to 0, and 1 for x less than 0. And I'm going to make g of x be the opposite. It's going to be 1 for x greater than or equal to 0. Sorry, I need a 0 in here. This is going to be 0. And this one up here is 0, and then this one becomes 1 down here. Now what is f times g going to be equal to? So it has a limit. But both of these don't. These are step functions. You know, you have one thing coming in and one thing going out. So they don't have the limit there at 0. And then, question.
You couldn't have done something like f of x is 1 over x and g of x is just x. And then together they just.
Except g of x has a limit at 0. They both have to not have limits. That's why I had to go with the step function. Yeah. But f over g is exactly going to be that. You're going to have f of x be 1 over x. G of x, you can make that be like 2 over x then. And then what is f over g?
It's a half.
Yeah, which has a limit. Yeah. So you have to be careful. Just because the product, sum, or quotient has limits doesn't mean the original functions have limits. We are done.
Wednesday, are we outlining in class?
Yeah, Wednesday we're actually not meeting in class. You can ask me questions on homework, but Wednesday you are doing the next outline, which is for section 2.4. And that is due before you leave for break. It's due by 10 o'clock Wednesday night. So that way you don't have a homework over break.
And so we're not doing
We don't
the
class.
homework for,
Yeah, we're not going to have class.
the homework for today.
It's due on Wednesday. Mhm.
Oh, it is. So
Yeah.
everything's still due, we're just.
Everything is still due, but we're actually not going to meet and have a lecture in class on Wednesday.
What about history of math?
We do
History and math, we're going to have class, and the homework will be due that night. But then there's really, I think the next week is research.
Like, why are we? Oh, because you don't want us to think about something like over break.
I'm trying to give you no homework over break.
Which we appreciate.
Yeah.
I, I like that idea.
I figure the majority of you are gonna try and travel, and if you're traveling on Friday and on Sunday, when are you doing your homework?
Never.
That's exactly right.
An hour before?
One hopes not. It takes a little more than an hour to do this stuff.
Have Dr. Anderson on the speed dial.
It's my problem.
No.
I know his number.
Well, I was trying to do the first one,
Right, good enough.
and like, I wasn't sure if I.
Knock on the door, ask her, you know what, I have an hour.
Let me show you the minutes for that.
Be my assistant.
Be my secretary.
No, wait.
Just have Dr. Anderson on speed dial.
This is our second form of the triangle inequality. You know this limit exists. Okay, so you know this limit exists.
Right.
So you know, you fix your epsilon. So you know there exists a delta such that for all x and z, you're going to have f of x minus L is less than epsilon. By your triangle inequality, you know this is less than or equal to that, but you know what's smaller than epsilon? Now, the only thing you have to have for the very end of it is notation. This is what you showed right up there.
Right.
But the L is equal to the limit as x goes to x naught of f of x. So that last line is just purely notation.
Okay. Okay, I know. I've heard this one.
I assume you guys had the same questions
No, I don't.
on the last one on this
Well-
section. I forget what the last one on that section is.
Let f from d to the reals with x and 0 as an accumulation point of d. Prove that f has a limit of x0 if for each epsilon greater than 0, there is a neighborhood q of x0 such that for any xy q intersection d, x is not equal to x0 and y is not equal to y plus 0. We have f of x minus y plus x.
Whenever you hear something in the form f of x minus f of y, you should think Cauchy.
Okay.
So what we're gonna do is we're gonna show that there's a Cauchy sequence for that one. What number is that? So you've written your hypothesis down. Yep. No, yeah, I'll look in my book. Okay, yeah. So I'm just thinking about how to make my Cauchy sequence. Okay, so I'll put it this way. For each epsilon equal to 1 over n in the naturals, I know that there exists a q, I'm going to call it a q sub n, contained in the reals, such that for all x, y, and q sub n intersecting in D, xn equal to x naught, y naught equal to x naught, we have f of x minus f of y is less than epsilon, which was y naught. So what we're going to do I'm gonna make this be positive. Choose delta n less than 1 over such that x naught minus delta n, x naught plus delta n is a subset of q sub n. Then for all x and y in x naught minus delta n, x naught, well, I'm gonna do it this way. I don't like this notation. When they put this neighborhood on there, I don't like that.
Very unimaginable.
No, that's it. Okay, then for all x, y in D with 0 less than x minus x naught less than delta n and 0 less than y minus x naught less than delta n, we have f of x minus f of y is less than y. Now I'm ready to make my sequence. So for each n in the naturals, let x n be in the interval x naught minus delta n, x naught plus delta n, x n not equal to x naught. Then I know that the sequence of xn it converges to x naught by construction. Because I'm forcing these delta n's to go to 0. The delta n's are smaller than 1 over n, they're going to 0. So these xn's are in this neighborhood around delta, around x naught, that are being forced to 0. So the sequence of xn is a sequence converging to x naught by construction. Now I'm going to fix epsilon greater than 0. Let n be in the naturals. Such that 1 over n is less than epsilon, so that I know the bound. I'm going to choose a speed n. Then I know that there is the delta n greater than 0. Such that I'm going to make this an epsilon exponent. Such that, I'll write it this way, x naught minus delta n, x naught plus delta n is subset of q sub n. So what we're going to do is choose our capital N in the naturals, such that 1 over capital N is less than delta n. And for all n, I'm going to call them too many n's for T and R greater than or equal to capital N. We have x, t, and x and r is in the interval x naught minus delta n, x naught plus delta n. Our hypothesis then, we know that f of x n minus f of x t minus f of x r is less than epsilon. Therefore, f is Cauchy. by, there's a theorem number that we proved last class period, Cauchy equals convergent. So you have to construct a Cauchy sequence. The hard part of that proof is actually the notation, getting to write your sequence, because the ends start rolling up and you get some random going around. But you have to just get around to construct your Cauchy sequence, show that f of x n is Cauchy, and then you know it converges. It looks terrible. It really, in theory, it's not that hard, but the process is tedious because I kept, wanting to use ends and I'd already used them, and so yeah.
I feel like it's interesting work and we think harder.
Mhm.
Because I feel like, oh, this is simple, and when you do it, and then you come to the question, and you're just like, I don't know where to start, and so you start going, and it's like, why didn't I think that? But then halfway through, I'm just like, wait, I couldn't have thought of this.
You could have, but it would have taken a long time. I mean, what we were studying in history and math, they didn't do that overnight. They played with those problems for years.
I have no patience for that.
People don't have the patience for that today. We have a lot of other things to do. All of our time-saving devices have made us so busy, we don't wrestle with things for great amounts of time anymore. I forgot to stop the video. It's now extra long.